the role of fluctuations in these systems that we've been discussing the last 2 days. And also, we're going to go back a little bit to the first lecture. So we are going to see ways in which we can approximate these master equations to obtain Fokker-Planck equations that we saw in the first lecture. I'm going to show you how to get that in a more rigorous way. There are 2 ways in which one can go from master equations. In which we can go from master equations to Fokker-Planck equations. You can find them in books by 2 names, Van Kampen's expansion and Kramers-Moyal expansion. We are going to study the Kramers-Moyal expansion because it's easier. Van Kampen's expansion is more powerful. But both of them are based on the same idea of assuming certain properties for the probability distribution function, which is basically the ones that we've been also thinking about in the last 2 lectures regarding the role of the relative variance of the distribution, the system size, and so on and so forth. Okay. If you are interested in studying more about Van Kampen's expansion, surprisingly, it's very well explained in Van Kampen's book. And the Kramers-Moyal expansion is very intuitive, so I don't think we will have any problem if you've been working with the exercises. So what is the key property that we are going to exploit to be able to perform this expansion is the structure that we have in the transition rates. So remember that we were discussing the role of nonlinearities in the transition rates. We introduced explicitly the system size, and it was basically because the rate at which these collisions happen, or these interactions happen, it's density dependent rather than number of particle dependent, right? So if we have a given number of particles, but they are within a very large system, it's clear that the interactions will happen, or collisions will happen more rarely. So what I'm going to do is I'm going to define a density. I'm going to call it X. That is going to be nothing else but the number of particles divided by my system size. And there are 2 or 3 questions that I got after last lecture, and they were many of you asked the same thing, so I think it's important maybe to answer them loudly. The first one was if I was choosing L square because I was talking about an island and therefore it's an area. Yes. In some books you will see L square and not even mentioning the number of dimensions. What is more common is that you will see omega as the parameter for system size. I don't like that because in many books you see omega for the transition rates, and that might be confusing. You can also use V. In principle, this is a system size, and the dimensions that it will have depends on the dimensions that your system has. If you are thinking about a 3-dimensional volume, then it's volume. If it's 2 dimensions, it's area. The second question that I got was regarding the moment approximation equations that we got for this master equation, and more specifically about the first moment equation that we got, that if you remember was something like this. Already after doing the approximation. And some of you were concerned because you've seen this kind of equation, and depending on the parameter that you have here, it may have chaos. And you were referring to this as a logistic map. So this is not a map. In the logistic map, time has to be discrete. And discrete time is a necessary condition for having chaos. This is a differential equation. Time is continuous. Nothing to do with, nothing. The phenomenology in this equation has nothing to do with the logistic map, okay? Don't be confused by that. And the third and final question, which was conceptually more important to clarify, is that many of you also refer to the time series that I was showing you from the simulations, if you remember. the fluctuating ones, as chaotic time series. And that worried me a little bit because what we are seeing here has nothing to do with chaos. Chaos, the chaos that you have in mind, is deterministic, which means that if you have a chaotic dynamical system and you know the exact initial condition, you can tell with full certainty where the system will be at any time, at any later time. The systems that we are studying are stochastic, which means that even if you prepare your system with an identical initial condition a given number of times, you cannot say what is going to be the value of where your system will be in its phase space at a later time. You can only give a probabilistic description of your system. Okay? So don't be confused between chaos and stochasticity, because that's a very common confusion, and it's not. Okay? In chaos, the point about chaos is that in principle you can never give the exact initial condition, and if you perturb your initial condition a tiny, tiny little bit, then trajectories diverge exponentially in time, and that's why you lose predictability, but the system, the dynamical system, is fully deterministic, okay? Sorry that I broke the flow of the lecture, but I was going to forget to clarify that, and that is important. Chaos is not stochastic, and then this is not a logistic map, and this kind of thing. Okay, so let's go back to the lecture. I am defining this density, and the next thing that I can do is I can write my transition rates in terms of densities instead of in terms of number of particles. So now basically, my transition rates, instead of going from n to n plus minus 1, they are going to go from x to 1 to x plus 1 divided by L squared. And that rate is going to be beta x L squared. And I have the same procedure for the other transition rate. And this is going to be delta x L squared plus gamma x minus 1 L squared. So if I write my transition rates in terms of densities, what is interesting is that the transition rates scale, all of them scale linearly with L squared. All of them scale linearly with the system size. And therefore, the approximation that I can do is that if L is much larger than 1, as we did in the last lecture, then I can write my rates like this. Great. An additional transformation that I need to consider is if I am defining a new variable x, in principle, I'm going to now replace, just to avoid some confusions, I'm going to redefine my probability distribution function, P2x. So is there any question up to here? All I'm doing is defining a new, I'm defining a density and I'm writing things in terms of the density. So now what I want to do is I want to try to write this master equation in terms of my new variable. And to do that, the first thing that I need to do is what? First thing I have to do is, well, given that I have this step operator, remember that this step operator I define it by applying it to a function of a discrete argument. And the only thing it was doing was to raise the argument of the function plus minus L. So in my density, let me use here the subscript x. This is all the step operator is going to do. And this is the conceptual important part. Once you understand this, the rest is math. The important thing is that by writing things in terms of the density, I have my system size explicitly in my equations. And if I take my system size to be large, then I can do expansions that I know they will converge on 1 over the system size, because that's a small parameter of my system. So if you remember all the very, very hand-wavy expansions that we did in the first class, to be able to reconstruct this overview of different descriptions of these stochastic systems, in none of them I was introducing this small parameter. And for many of these expansions, actually some of you asked me in the afternoon, in principle I shouldn't be fully sure that they will converge, right? Because, I mean, I have no control on what is that I am using to do these expansions. Now I can expand these. And here we can make it, if you want, a little bit more explicitly. So we have all the signs. And I have L, so they should be L plus L square to L square, 4, F with respect to X square. And then I have terms that are going to be order L6. So if I stop my expansion at order L to the power of 6, then I can rewrite it in a way that will very easily allow me to identify this as the expansion of my step operator over X, right? Yes, question. This? So here I have right? Yes. So what I am saying is that this when the system size is large, basically x squared minus x goes like x squared. Yes. Huh? Ah, yeah, sorry. Yeah, I did run the, yeah. Yeah, no, wait. So I have gamma, yeah, sorry. This is gamma x L squared. Yeah, sorry. Gamma x, because I have 1 L squared above, below x squared minus 1. Yeah, sorry. And then I kill the 1 here, and I have, yes, thank you. Yes. That's what I'm going to do. Yes. So this is an important, very important question. Now are we talking about x as a continuous variable? What I'm going to do is I'm defining a density that in principle, if my system is not large, is discrete. And as I take L large, then x is a continuous variable. And that's why you will see that this Kramers-Moyal expansion to the master equation, it's also called a diffusion approximation. Because basically what it does is to approximate the random walk process in N by a diffusive process like the one we described when the first day I defined this omega sub epsilon stochastic process that had a triangular function, and then we took tau to 0. So what we are doing is the same kind of approximation in which we go from a discrete variable to a continuous one, but with a general master equation. Yes. So now basically all you have to do is to replace this expansion of the step operator into the original master equation. And this is what you will get. Which, if you have already started to do the exercises, which I hope you did, I know many of you actually did, this equation that you will arrive at which you will arrive after replacing the expansion of the step operator has the same structure of the equation that I was asking you to prove in problem number 1. So basically, what you have now in this equation that is a generalization, if you want to think in those terms of the diffusion equation that we derived in the first lecture for the symmetric random walk, is an equation that has an advection term and a diffusion term. And notice that the transition rates, they are proportional to L squared. So let me already, we can use here yellow. So we have an advection term and a diffusion term. Who wants to explain me what is the role that these two terms are going to have in the dynamics of this system? Anyone has an intuition? No, I canceled the L square and the L fourth because, well, this is going to be proportional to L square here, and they will go out. So here, here, if I don't replace the omegas, they don't cancel, of course, because omegas have the L square. So maybe instead of cancel, let's do something to avoid problems. Let's just circle them, because we're going to discuss about them, but they don't cancel. That's true. So what do you think is the meaning of each of the terms in this equation? What does advection do in an equation, in general, when you have, I don't know, a PDE and you have an advection term? So this first term, the advection term, what it's going to do is going to reflect the deterministic part of the dynamics. So basically, if we start, let's say, with a given initial condition for our probability distribution function, the first term, what it's going to do is to translate that probability distribution function. If we didn't have diffusion, we would see the same width of the probability distribution function, just moving in the coordinate x in this case. Remember the case we studied the first day in which we had a symmetric random walk, and I told you R is equal to L, it's equal to 1/2, or we said M. In that symmetric case in which the omega that takes my random variable going to the right or to the left are the same, then this term cancels. That's what we see the first day, because on average, my random variable does not change. I only have diffusion. But that is a very important point that is reflected in the structure of this second term, which is the diffusion term. That is that even if you have the same transition rates to the left and to the right, and for the advection they will cancel, in the fluctuations they never cancel. Right? That's why if you have, let's say, I don't know, a birth-death process like the one we defined the first day, linear, that we were able to solve, if you remember, this two-level system in which particles were going from state A to state B. In any of these processes, if you, let's say, multiply your rates by a factor 2, by a factor 3, by a factor 4, all of them, like keeping them with the same relative value, but just increasing the value. So imagine that we say, I have beta equal to 1 and delta equal to 0.5. And now we have beta equal to 2 and delta equal to 1. This may not affect at all the deterministic part of my system, but we need to be careful with the fluctuations, because you see that they go as the sum of the rates, not as the difference of the rates, okay? So in the notes that you have online, and in many other books, they refer to this term as the drift, and this term is the diffusion. What is the second interesting thing that you see here in this equation? Let's actually, maybe to make that clear, more clear, in case you had a long night of study yesterday and you're still so let us replace these omegas by the values that we have for our specific example. And now I can actually kill the L squares. So what is something interesting that takes your attention in this, the structure of this equation, or the terms of this equation? It's a nonlinear equation. Yeah, that's true. It's nonlinear because the rates were nonlinear, right? Yeah, if the system size is very big, this term here will be negligible, basically, right? And if you think carefully, or if you are sufficiently awake already, this term that I have here is nothing else but the equation that we derived on Wednesday for the mean number of particles after rescaling it by L squared. If you go back to your notes, you will realize that from here, you can see the same structure that we saw in the ordinary differential equation for the mean value of particles. Yes. Well, here, because here I have, yeah, I have this is the term that will drive the dynamics of my mean value, yes. But related to that question, then on Monday, we went for the Fokker-Planck equation, which I told you was a deterministic equation for the probability distribution function of a random variable x, but the equation itself is deterministic, which means that if I give you p x t equal to 0, and you are able to integrate this partial differential equation, you will know, in this case, not all the information about the system, because we are already doing an approximation to get the Fokker-Planck equation, but you will reconstruct the probability distribution function for your random variable x. And given an initial condition, you know the distribution at any time. But we also saw that an alternative way of describing stochastic dynamics is with equations that describe stochastic differential equations, that instead of describing the dynamics of the probability distribution function, describe the trajectory of the system. So now, instead of having a partial differential equation for the probability distribution function, I should have a differential equation for the density x. We don't have time to do the whole derivation of how you get from the Fokker-Planck equation to the master equation. In the notes I shared with you, it's there. And it's not it's like a long calculation where you need to use like functional calculus and some theorems from stochastic processes. So it's not a very straightforward thing to learn maybe in the undergrad. But just to be able to discuss it a little bit, if I call this term here A and this one here D, so you can prove, and again, if you are interested, you can look at the notes, that if you have a Fokker-Planck equation with this structure, then the corresponding Langevin stochastic differential equation has this structure. So basically, as we were discussing, the advection term will, it's going to become the deterministic part of the dynamics, and the diffusion term is going to become the variance of the stochastic part. And this psi here is the white noise process that we derived on Monday. There are some subtleties in this derivation if you read the notes, and that's why I didn't went into this calculation with a lot of detail, because some of these integrals, when they involve this stochastic process, they are not well defined, and you need to interpret the noise in different ways. I don't want to enter into that for those of you that are not familiar with this. Those of you that are familiar with this, I want to reinforce that for you. And this is you will see in the books, is the ETO interpretation of the noise. I'm not going to enter more into this way of describing stochastic systems in this course, but I wanted you to, again, have in mind that once we have this description for the stochastic process, that, remember, comes from expanding the master equation, we can write still a stochastic differential equation. And again, as we were saying before, when L is very large, then the fluctuations will be negligible, and I recover a deterministic dynamical system like the one that we recovered when we were doing the moment approximation in our equation. Okay? That's all I'm going to talk about these equations. But before doing that, I want to ask you, besides the general structure of these equations, for the particular choices of A and D, sorry, this is D, let's say diffusion. For the particular structure that we have now in this problem, what do you observe? For example, which kind of dynamics would you expect in this equation? I don't know, maybe the question is not very clear, but do you see some property of this equation just because of the rates that I have that take your attention? We discussed that last day. I just want to remember that to remind that for you. What happens if I plug x equal to 0 here? So in principle, if I do, let's say, I take this equation and I run a numerical simulation of these dynamics, what you probably are expecting is that you will have here x, you will have here time, and I don't know, you start with a given x, and then you do your simulations, and then you get a stochastic time series like the one I was showing you before. Then you do a different initial condition, and you get the same initial condition, but you can get a different thing, and then it fluctuates all over the place, and it's fluctuating forever. But if you look at the structure of this equation, when x is equal to 0, both the deterministic part, the drift, and the fluctuations vanish. Right? That means that if your realizations hit 0, they will stay there forever. And that doesn't happen for the fixed point or the stationary value of the deterministic description that we derived the other day, right? If you plug here, I think it was B minus delta divided by gamma, this term will not cancel, of course, because fluctuations always add up. They don't cancel. Right? But if you substitute here the 0, the absence of populations, then your system will get stuck, will get frozen in that state. How many of you have studied this type of states in physics in your courses? So this is an absorbing state. And probably if you, the first time you, I don't know, because I don't know how it's in your countries, but when you start studying non-equilibrium statistical physics, one of the very first systems you will see is a system that has one absorbing state. Because absorbing states violate the detailed balance condition, right? Because probably the system goes there but cannot leave. Questions? Absorbing states, basically the dynamics, the system can go there, but it cannot leave. So it's an example of a non-equilibrium system. Yes? You can derive it from here. And it's related to the same derivation we did on Monday. But now, of course, you are going to, if you go through the notes, you are going to have a more general case. And it's not, you cannot define an omega epsilon and take the limit. It's based on like more advanced math. Right, so just to finish, I wanted to discuss with you a type of analysis that it's very common both in physics, in biology, and even in economy, in the stock market, in finances, whenever we have, for example, states that are particularly relevant, like absorbing states. That doesn't mean that we can only do the calculation that we are going to do when we have an absorbing state, but usually absorbing states are relevant for the dynamics. In this case, for example, in this very simple population dynamics example that we have, the absorbing state x equal to 0 represents that my population dies, no? It goes extinct. So therefore, it's interesting for us to ask questions about that particular state. For example, if we are interested in, I don't know, working with the government for conserving that a given species, or in the market, in the stock market, for example, a lot of these analyses are done when you want to set a price, after which you are going to sell your actions, your stocks. Then you are interested in calculating, for example, what is the probability that my stocks reach, I don't know, 5,000 reais, or when will you do that, and so on and so forth. So that's what we're going to do to just in the last 25 minutes, probably a little less, so we have more time for questions. Any question from up to here, sorry? No? All these coins, these crypto coins. Yeah. And then they get, yeah. Yeah, actually, what do you think is the role of the system size in these probabilities of reaching absorbing states before I clean it? So imagine that we have a very large system, and we start with a very high X, very large system, very high X, and the absorbing state is in 0. Do you think that would make my system easy? It would make it for my system easy or hard to reach the absorbing state? Let's try to make a cartoon. So this is my absorbing state, 0. And I start with a given X and a system size L1. I don't need answers, I just need you to think. Or I start with a system size L2. Remember that X is system independent, right? This is what we had, the plots that we had on Wednesday, right? So think a little bit about how my fluctuations, even if I start with the same intensive variable, X, how my fluctuations, my system size, will affect the actual stochastic dynamics of my system. That's a very interesting question, especially if you start studying statistical mechanics and you start doing things like finite size analysis, scaling laws, and these kind of things. I think it's interesting for you to sit down and spend some time thinking about the structure of this equation, the fact that intensive variables like densities don't depend on system size, but this term does, how that changes the... I don't need answers. I just need you to think, and the good thing is that I'm leaving very shortly after the lecture, so you just need to think and yeah. But yes, basically, the larger the... Yeah. That's, well, if you start in your initial state, in an absorbing state, you start there forever. Is that your question? So this is a very important question. The question is if the absorbing state is not something we imposed, is the result of the rules that we put. Is that your question? Yes. So the existence of the absorbing state comes given by the rules of my system, right? It's just because when n is equal to 0, all these rates are equal to 0. Then there is a whole, and I don't want to enter too much into that, but usually you can classify systems depending on, for example, there is a series of models in physics that will have two symmetric absorbing states. Instead of 0, imagine +1 and -1 are absorbing states. And those systems will have different properties than those having only one absorbing state, as it is this case. And you can classify systems or models that have these given symmetries in universality classes, for example, in statistical mechanics, which means that they share some properties, some critical properties. So the existence and nature of absorbing states in this type of models is very important. Okay? It's determined by very often by the symmetries of the microscopic dynamics that you have. Yes? How do, sorry? So if you want to obtain it formally, so the question is, how do you obtain the stochastic differential equation? That was getting this question was because my fear when I thought whether showing this or not, in the sense that it's not very easy to give you a straightforward answer. But basically what you would need to do is, considering the probability distribution function, you need to ask questions related to what is the probability that you sample a given trajectory. And then basically you need to consider the probability distribution function as an average over trajectories. And applying functional calculus, you will obtain that, the Langevin equation. I think it's the best thing for you to do if you're interested is to, I think in the notes that I share with you, I think it's chapter 7 or that explains step by step how to go. But step by step means that, of course, between steps you have to do a lot of math. Yes.
I understand how would a system look like if the drift is 0. It's the first example we did.
Yes.
But how would it look if the diffusion is 0?
How would the system look if the diffusion is 0? That's the main reason why I took the risk of writing down this equation, even though I acknowledge it could open questions on how I go from one place to the other. So just look at your equation. How do you think your dynamics will look like if diffusion is 0? So the diffusion is multiplying the only source of stochasticity in my model. So if diffusion is 0, I mean, I wrote the equation like this. You will also sometimes see it written just with the white noise and introducing the in the correlation function of the noise. Maybe that will help you interpret. So basically, if the diffusion is 0, what will mean is that the variance of the noise is 0, the amplitude of the noise is 0, and your system behaves deterministically. Okay, so let's go quickly through that calculation because I have 15 minutes and I want to at least so we are going to see how can we tackle that problem of first hitting times. That's how they are called. Of first passage times. There is a if you are interested in these problems, now that we discuss them, I can share with you a few references that are well, are the most common to study these problems. So let's discuss first passage problems. Great. So we are going to do that with the symmetric random walk because it's much easier. And at the end, all I want is to help you develop intuition. Oops. So on Monday, we had this symmetric random walk in discrete space with lattice size A and then time step tau. And we never said anything about the system, right? It was an infinite system. The particle was jumping left and right forever, and nothing happened. To calculate these kind of first passage problems, let's bound the space, or the domain in which our random walk is going to move, say between 0 and L. An interesting exercise that you can do to make sure that you understood how to solve these problems is this afternoon you sit down and you say, well, now instead of using a finite domain, I'm going to use a semi-infinite domain and I'm going to calculate the probability that it hits 0. And then you can try to see how far you get. And remember, when the particle is here, it jumps left and right with probability 1/2. But here, in 0 and L, let's assume absorbing boundaries, which means that once the particle reaches one of these extremes, then the probability that it will move left or right is 0. Okay? Do we have any idea on the room on how to attack this problem? I'm interested, let's try to obtain what is the probability. Let me keep notation like always. What is the probability that I hit 0 starting from the node I? This is the probability of hitting 0 with initial condition at I. If you wait long enough, if you start throwing coins or put this in a computer, the probability that I hit either 0 or 1 as time goes infinity is going to be 1, right? So the system eventually, the random walk is going to hit one of the borders. That we already know. So the probability that starting at I hit 0 plus the probability that I stay is equal to 1 for all I, regardless of the initial condition. Yes?
What's the 0i?
So this is the probability that I hit 0, of course, before hitting L, because if I hit L, then I die, and I never hit 0. Starting my random walk at node I. So let's say this is not node I. So if my particle was initially here, I'm interested in calculating what is the probability that I will hit 0, of course, before I hit L, because if I hit L, I will never get to 0. Any idea? So my first idea is to say the probability that I hit 0 if I start at 0 is 1. That is my brilliant contribution. Anyone? Trying to write a master equation. Okay. Yeah, no, but you're going in the right direction. Or at least in, yeah. That would be, yeah, that would be, yeah, that would be related to counting paths, no? The first question we had. Yes, so trying to go in that direction. Does anyone want to tell me what is the probability that I hit 0 when I start at 1? 1/2. 1/2. Plus? Plus the probability that I go right is 1/2. And then? Plus the probability that I hit 0 from 1. From 2, yeah. From 2. Yes, sorry. I just wanted to see if you really understood it. Why can I do this? Why can I do this? This is a technical clarification that we need to make. But why? Why? because my random walk has no memory. Okay, so this is related to the Markovian property that we defined the first day. If your random walk has memory, you cannot do this. But yes, so once I do the first step, then my process, I just add probability and my process is the same. So in principle, what is the probability that I hit 0 if I start at I? And then, of course, I have the final one, that is the one I make like I do, because it's like always the easy one, is the probability that I hit 0. If I start from L, it's 0, no? Because if I am already in L, I will never get to 0. These are boundary conditions, no? And these is a recurrence relationship that I can solve. Have you solved this kind of recurrence relationships? Okay. Then I can give you, well, if you haven't, I think all I can do is also give you the result and the. So, what you will get is that the probability of hitting 0 starting at I is equal to A plus BI, where A and B are constants that come from solving the recurrence relationship. And remember that then we have the two boundary conditions that you need to apply here to obtain the constants. And then we get the probability of hitting 0 starting from I is A is equal to 0. It's it's 1 minus I divided by L. So I don't know if you are going to ask me why did I choose 0. Well, I could do the same exercise with L, and then you get a different result, and then just applying the conservation of the total probability, the probability of hitting L starting from 0 is I divided by L, of course. So this is L, this is P of hitting 0, this is P starting I. And basically your probabilities are not very interesting. Well, this should hit 0 here, of course. But it's not very like amazing figure, but that's what it is. That's what we get for the symmetric random walk. This is the probability that I hit a given border of my domain. Another question that is very, very common is when. When will I hit this border? Because sometimes, well, we also need information about the time. Yes? No, because I solved this. You solve this, and then you get the solution of the recurrence equation. You can do it with assuming an ansatz R. You have to obtain the characteristic polynomial, and then you will see that it has repeated roots as you do in differential equations, and then this is the general solution, and then you use boundary conditions. So there is math. From here to here, you need to solve the recurrence relationship. That's why I ask you if you've solved it before. Okay, you need to solve it. So how would you do for the time? The time is a little bit more interesting. Just intuitively, here it's fine. I mean, we don't need to be extremely creative to realize that what this result, for example, is telling us is that if my initial condition is in L divided by 2, I have, let's say, the highest uncertainty on which border will I reach. Both of them are equally likely. Well, that's fine. With the time, things are a little bit more interesting. What do you think would be an interesting difference between probabilities and time? well, let's write the equation. Maybe that question is. So what is the time, the average time? This is the mean time. Huh? This is important. Why is this important? It's the mean time to get to the border because time, the time it will take me to hit the border, is also a stochastic process. Right? Do we all get that? The time in this discrete case is the number of steps. But if you think, for example, on this stochastic differential equation I wrote before, it can have actual dimensions of time, and it can be time, like a proper continuous time. Is it clear for everyone that this time I will need to hit one of the borders is a random variable as well? And it will have its own probability distribution function. And you can write a Fokker-Planck equation for it. And you can do the same thing you would do with these birth-death processes that we saw. They are way, way more complicated to characterize because it's a random variable given by an underlying random variable. So then it's trickier. Okay. So let's focus on the mean of this time. So what would you think is the time I need to hit 0 when I start at 0? 0. Okay, what is the time if I start at 1? What is the time I need to reach 0 if I start at 1? I will never reach 1? Why? No, 0 is an absorbing state. 0 and L are absorbing states. Yeah, so it's 1 plus, well, 1 or tau, depends how do you find the time, right? It's the time it took you 1 step plus the time from reaching 0 from 2. Need to divide by 2. Why? Yes. I need to take into account that the probability that I get the neighbor times the time I reach it from the neighbor. Yeah. Why can I write this like this? Again, because my random walk is Markovian and the mean value is a linear operator. Yes. Because if I am in 1, the time I will need to reach 0, in general, is going to be the time of making 1 step plus the average time to get to 0 from the neighbors, because I need to account for the time I'm using to make the step. That is the key difference. That here I was only asking about probabilities, but here now I need to account for the time. And that, at the end, is going to introduce an additional term in my recurrence relationship, which is this one here. So in general, the time it will take you to reach 0 from I is equal to 1 plus 1/2 t plus I plus 1 plus 1/2 t I minus 1, 0, and 0. So this is a recurrence relationship that is very, very similar to the one we got for the probability, but the difference is that now it's not homogeneous, so when you solve it, you need to solve for the general solution, and then you need to find a particular solution. And but the math is the same. So just to finish in time, sorry, actually, yeah. So this is only valid, I don't know if it is related to your question. This is only valid when I don't care about which border I take. Sorry, I should have said that from the beginning. Let's recap. So I'm interested in the probability of reaching one border, no matter which one it is. So then, the probability that I reach it from 0 is 0. The probability that I reach it from 1 is 1, plus the probability I reach it from the neighbors. And the probability, the time I reach one of the borders starting from L is also going to be 0 in this case, because I don't care which one of the borders. You can repeat the calculation that I was sketching, like what is the time I will reach 0 starting from 0, but it's a little bit more complicated and it is longer. Okay, sorry. That part was confusing. Anyway, once you solve this recurrence relationship, you will get something like this. That has a maximum, of course, as we should expect when the initial condition is in the middle of my system. Questions? Yes. Here? So here is because you can decompose your random walk. So basically the probability that you reach 0 starting from 1 is 1/2, one step, plus the probability that you reach it from 2. And then, yes. So the probability that you reach it from 2 is encoded in the next equation, and then it's how you build the recurrence relationship. So you need to write an equation for that, but it's independent from, and then it's how you construct the hierarchy of equations. So if you, the thing is that you can write it general for any I and solve it for any I. But yeah, in principle, you can write it for 1, for 2, for 3, for 4, and solve one by one and plug the solution of one on the other, and so on and so forth. But you write it for general I, and then you solve. Yeah, questions? Why you multiply it by 1/2 the? Here? Why? Because you need to take into account what is the probability that you reach T2 and then the time that you, because it's a mean value, right? It's the mean time. It's not the time is a stochastic process, and you're writing equations for the mean value. But this is the time you will. So if you have, this part was a little rush. If you want to discuss it in more detail, I will be here in the afternoon in the problem session, okay? I would like you to ask also to make sure you understand this part, the one with the probabilities, more intuitive. And if you understand this, maybe you can do the calculation with a semi-infinite domain. And then once you get yourself familiar with that, that one you will see it's a generalization. It's an extension, not an questions? Cheers. So the only problem that was left in the sheet that there were the last question of problem number 6, I think it was? No. The one about solving a master equation which solution was a Poisson distribution. 5, the last question of that problem was asking you to write the Fokker-Planck and the master equation. Some of you were trying to do that. Now you can do it if you want. And then the final problem was a two-dimensional problem that I thought some of you may be wondering, how do you generalize these things to more dimensions? In principle, you should be able to do it as well. The only thing that you need to do is to expand the step operator with 2 variables, basically. So you need to write a master equation for x and y, or wherever you call your two variables. And then when you expand, you need to define master equations in x and in y, and then you expand master equations in x and y, and so on and so forth. Okay? If you want to try that one and have any question, I will be here today until, I don't know, long enough, probably 5:30, 6, I still will be here. Okay? And an interesting thing of high-dimensional systems is that in your diffusion term, the one that was multiplying the noise, you may have cross terms. So it's not a scalar anymore. Now you have a diffusion matrix, and that diffusion matrix will have both diagonal elements that will tell you the amplitude of the fluctuation of each variable, but it will also have off-diagonal terms that will tell you how one variable change is correlated with the other. So it will basically give you dependence between variables, interdependence between both variables. Okay? More questions? No? Well, if you have them in the afternoon, if I'm not in the problem room, my office is 105. It's right in front of the elevator in the first floor. Okay? Just come there and ask me if you have any other question.